Okay, so good morning everyone. So last class we were looking at relation between circuit classes and uniform complexity classes. Okay, we saw results like NC1 is uniform NC1 is contained in L and all of NL is contained in NC2, and of course there are these uh, containments that follow somewhat by definition. For example, that NC1 or for any NCI is contained in ACI. Essentially, bounded Fanon circuits can be simulated by unbounded Fanon circuits. But the point is, if we are allowing unbounded Fanon, can we actually shrink the depth, okay, from some d to something smaller than d, okay, and that is exactly what this theorem is characterizing. That if I take a d depth circuit of bounded Fanon, then I can construct another equivalent circuit which has unbounded Fanon, but depth d by k for any parameter k. Okay, so k is something that we can choose as long as it is smaller than d. Of course, yeah, if it is bigger than d, then it does not make much sense, because yeah. So I can choose d to be smaller and I compress the depth, and of course there is a blow up in size from s to 2s d times 2 to the power 2 to the power k plus 1, but for small enough k this would still be manageable for us. Okay, so we will see what kind of things we can choose. So let us see how the proof goes. So the idea of the proof is quite simple. So okay, so we have the circuit C. Okay, so let's just, okay, let me draw a picture first. So we have this circuit C, and if I take, okay, so this is my circuit C. If I take any level, so let us say that C is layered in some sense. Okay, so by layered, what we mean is that the gates, so basically every edge of the circuit goes from one level to the another. Okay, so I can partition the gates into layers or levels, and every edge goes from a level I to I plus 1. Now if I look at any level I in this layered circuit, and let us say I look at, okay, maybe let us say I look at I plus C, and I have I over here, I plus K and I over here, then I can somehow represent the output of a gate in I plus K in terms of the gates in level I, okay, up to a depth K. And how will it be? So this is a bounded Fanon circuit. Let us assume, without loss of generality, that the bound is 2. Okay, so we can assume that these are AND or and NOT gates, so over which takes 2 inputs at most. So then basically every gate here would somehow depend on at most 2 to the power k. So this is depth k, so 2 to the power k gates from level I. Okay, and this is basically the idea that we want to exploit. So the point is that it cannot depend on arbitrary many gates from level I, but a small number of gates, and this is what we will exploit to design a smaller circuit. Okay, so okay, I'll give the argument. Okay, so this is just informally I'm saying. So informally, basically, if I look at this thing, so every gate here has at most 2 inputs. So if I go down by a level k, it can, I mean the tree can have at most 2 to the power k leaves of depth k. If I take any tree of depth k or any graph of depth k, it can have at most 2 to the power k leaves. That is what I am using. Okay. So we will construct a circuit C prime as follows. So the first step of the construction is to make sure that we can assume it is layered. Okay. So firstly, make C layered by introducing dummy identity gates. Okay. So, essentially what I am saying is that let us say suppose I have an edge which is going from some layer I to some layer j, okay, and j is let us say greater than I. Then what I will do is that I will introduce some dummy nodes over here, dummy gates over here, which are identity gates. Essentially whatever they take as input, they just send the same thing as output. Okay. So, this is to make it layered. Okay. So, whatever, so there basically I will be adding how many j minus I minus 1 many such dummy nodes for every such edge. Okay. So, initially my size was S and depth was D. So, after layering, the size of the circuit is at most S times T. So, there are, so S you can think of it as the number of edges in the circuit, okay, so it is a DAG. So, the size of a DAG I can assume it to be the number of edges, and for every edge at worst case I will be adding D many dummy nodes. So, therefore, it is at most S times D. Now, what I will do is that replace levels I to I plus k using a DNF circuit. So, essentially I take a gate over here, okay, and as I said that I will look at all the gates in level I, and I can basically replace it with a DNF circuit. Okay. So, I can think of it as a truth table. So, okay. So, how many inputs will it depend on? So, every gate in layer I plus k will depend on at most 2 to the power gates of layer I. Okay. So, essentially you can think of it as a truth table which has 2 to the power k inputs. Okay. And now the size of this truth table will be 2 to the power k. Okay. So, essentially if I am doing a DNF, so I have a OR gate at the top. This OR gate will be an AND of 2 to the power k many. So, this OR gate is basically a combination of 2 to the power k many AND gates, and each AND gate can have at most 2 to the power k variables from this layer. So, essentially, okay, so let me write this down. So, the top OR gate will have at most 2 to the power k inputs and every AND gate below it will depend on at most 2 to the power k inputs. Okay. So, basically you can think of it as I have a truth table over 2 to the power k many variables. So, if I want to do a DNF of this truth table, this is basically the size, okay, and then at the bottom I have literals which are either direct edges or maybe not of something. Okay. So, is this clear? So, essentially what I have done is I have reduced okay. Now, okay. So, essentially what am I doing here? So, okay. So, maybe I could have done, I should have said this earlier, but I can say it. So, C is divided into, in fact this is not tree exactly, let me write this as a note. C is divided into D by K blocks of K layers each. Okay. So, again pictorially this is what it looks like. So, this was my C. So, I have broken down into the first block of K layers, then again I have K over here and so on, K over here, and the total number of such blocks is D by K, and for each block I am essentially doing this kind of a replacement. Okay. So, each block of K layers I am replacing it with a 3 layered circuit. Okay. So, we will count how many nodes are increasing. So, right now what we have done has reduced C prime from depth D to 3D by K, correct. Now, what about the size? How much does the size increase? Okay. So, after the depth reduction for each gate in layer I plus k, the size of the DNF circuit is at most. So, what does the size of the DNF circuit look like? So, I have so basically I can take any one block and basically I am expanding it to, so I have a OR gate at the top. So, this OR gate depends on 2 to the power k many AND gates, and these AND gates will depend on each AND gate will depend on 2 to the power k many gates from layer I. So, what is the blow up in the size? So, now basically for each gate my size is 2 to the power k many AND gates plus 1 OR gate, right. And of course, I will also be having the NOT gates, but let us just, I am just counting the AND and OR gates, let us say, for the time being. Just write it over here, the AND OR size of the DNF circuit is at most this much. Okay. Now, using De Morgan's, so now I will have some NOT gates, but I can actually shift all the NOT gates to the bottom by using De Morgan's theorem. We can shift all NOT gates to the input level with at most doubling the size. Okay. So, therefore, what we get is, so therefore, we have that depth of C prime is, what is the depth? So, there are D by K layers. So, for every D by K blocks, so for every D by K blocks, I have 2 layers now, and then finally, I have an additional layer at the bottom of NOT gates. So, this is the depth, and the size is S. So, this I am doing for every gate. So, this is SD. So, when I layered it, the size went up to at most S times D. So, it is SD times 2 to the power 2 to the power k plus 1, and because of applying De Morgan's theorem, this is at most twice. Okay. This is a upper bound. So, this proves the theorem. Okay. So, as I said, the idea is actually quite simple. It is just replacing some small depth with a corresponding DNF formula or DNF circuit. Okay, so now as I said last time as well, an immediate corollary is that what we can show, or every function in NCK can be simulated by a circuit by an unbounded Fanon circuit of polynomial size and depth order log to the power k n divided by log n, and the proof is very simple. So, you just take k to be equal to log n, that is it. So, if you take k to be equal to log n, then S times D, which is anyway bounded by a polynomial, times 2 to the power 2 to the power k, which is just n, plus 1 will still be a polynomial, but now the new depth is D by k, which is polylog divided by log n. Okay. So, this is improving upon the observation that NCI is in ACI. Okay. Any questions? I mean, it is reducing by a factor of k. and you can take k to be anything. If you want the size to be polynomial, then you can take k at most log n, because if you take k to be anything bigger than log n, then 2 to the power 2 to the power k will be bigger than polynomial. So, the next thing that we will study is, so we have looked at circuits that are polynomial size but bounded depth. So, now we can just generalize this to any circuit of polynomial size. So, this class P by poly is the class of functions for which there is a polynomial sized circuit family. Okay. So, we do not have any restrictions on the depth, it is just any polynomial size circuit family. Okay. So, now the question is, we have seen relation between these bounded depth circuit classes and uniform classes. What can we say is the relation between, for example, P and P slash poly. Okay. So, that is what we are going to see. So, this is again a sort of an application of okay, I'll come to that. Let me just state the theorem. So, we will prove the following theorem, that let L be a language decided by a Turing machine running in time t of n, then L can be computed by a circuit family of size order T of n square. Okay. So, if you have seen Cook-Levin's theorem, okay, to show that SAT is NP hard. So, this is essentially along the same lines as Cook-Levin's theorem. Okay. So, essentially we take a Turing machine which has a certain running time. So, now this has deterministic running time. So, L is decided by Turing machine which has deterministic running time T of n, and I will look at the different configurations of this Turing machine for different levels, and I will try to build a circuit by looking at this matrix of configurations. Okay. So, essentially that is the idea. So, I will just quickly go over the proof, because yeah, I mean if you have seen it, then you can, it is good to have revisit it again, but otherwise I will skip maybe some details and that can easily be filled up. Okay. So, let us look at a sketch of the proof. Okay, start here. Let L be decided by a Turing machine M equal to Q sigma delta Q naught F having running time T of n. So, Q is the number of states, this is the alphabet size, this is the transition function, start state and the number of accept state, and we will assume again without loss of generality, that the Turing machine has a single tape. Okay. So, it has a single tape. Initially we only have the input x written on the tape, everything else is blank. What else do we need to assume? Yeah, I think that is good enough for us. Okay. So, now so what is the transition function of the Turing machine looks like? So, the transition function of a deterministic Turing machine can be thought of as a function from q cross sigma to q cross sigma cross L comma r. So, essentially what this is saying is that at every time instant when I apply delta, the Turing machine looks at the current state. So, basically there is a head in the tape. Okay. So, it looks at the current state, it looks at the input being pointed to by the head, and then it moves to some other state, it replaces that character with some other character, and the head moves either left or right. Okay. So, that is what we will assume delta does for us. So, now it is easy to see that delta is actually independent of the input. Okay. So, delta is basically a constant sized function, because all these are bounded sets q, sigma. So, both of them are sets of bounded size. So, the first observation is that delta can be represented by a constant sized circuit, and when I say constant, I mean that it is independent of the input. So, essentially it is a circuit which looks like this. Okay. So, let us give it a name, let us call it as C delta. So, C delta takes as input some q in q, and let us say some a in sigma, and then it outputs some, well not some, but the q prime corresponding to whatever delta is. So, it outputs a q prime in q, it outputs a prime in sigma, and it let us say outputs whether to go, it outputs a bit which says whether you have to go left or right on this. Okay. And just for the sake of I mean ease of implementation, you can assume now that the circuit that we will be building has alphabet which are elements from capital Q, sigma, L, R, okay, all these. So, this is anyway a bounded set. So, but you can assume the alphabet to be over this, and then finally you can just replace all of this with strings over 0, 1. It does not matter, I mean it is the same thing. Okay. So, now what do we do? Okay. So, consider a Tn cross Tn matrix, say, let me not use M, I have already used M over here, let us say P, okay. Where the ith row of P represents the configuration of M at ith time step. Okay. So, now what is a configuration? So, a configuration of a machine consists of three things. Okay. So, a configuration consists of firstly the current state, secondly the tape contents, and thirdly the position of tape head. Okay. So, we will see a method to encode all these three things into the Turing machine. Okay. So, now note that, so the longest, so of course, the state is a constant thing, but the tape content, so at any point in time the number of cells used in this machine M can never exceed T of n, because that is the total running time. You cannot write beyond T of n, T of nth cell, you cannot go that far, because at every step you can only move by one step. And the number of rows is of course the running time, because the running time is bounded by T of n, therefore the number of rows is bounded by T of n, and the number of columns is also bounded by T of n. Now, let me be a little bit more specific about the contents of the rows, sorry, the contents of the entries. So, P of I comma j will store the following. So, firstly it will store the letter in cell J at I will write this later on, the letter in cell J. Secondly, it because, okay, just let me complete this, then it will be easier. I mean, I am just describing what the matrix is. Let me complete the description, it will be easier then. Let me just change this a little bit. So, the first one will be the whether the head points to cell J so this I can call as, what do I have it as, head present bit. So, this is a single bit which stores this. Second is the letter in cell J, and the third is the current state. Okay. So, these two together will be the data part, and this is the head present bit. Okay. And all the above are for time step I. Okay. Okay. So now coming back to your question, why is the number of columns bounded by Tn? Okay, because see, what are we storing in this matrix? So in this matrix, essentially we are storing the information about cell J. Okay, so whether the head is pointing to cell J or not at any time I, what is the letter in cell J again at any time stamp I, and what is the current state when it is at when the head is pointing over here. If we, I mean, if the head is not pointing, the current state does not matter, but anyway we can keep something. What is the current state? Okay. Now the point is that if the machine has a running time Tn, okay, then at no point in time can basically it go beyond Tn many cells. Okay, at no point during its computation, because at each step it can only move one bit. So even if we assume that at each step it moves left, it moves right, it can only go up to Tnth cell. So we do not have to store anything beyond, we do not have to store any information of any cell beyond T of n. And once we have stored this, note that this actually represents a configuration, because I have the current state. By looking at the entire row, I know the tape contents, okay, that is from this second point, and the position of the tape head is obtained by again looking at the entire row and seeing for which J is the head present bit set. Okay. So now we will see how we design a circuit. Okay. So the next step is note that any entry of Pij, what does it depend on? What does an entry of this matrix depend on? Huh? Pi minus 1, that is the previous row, and so in terms of the matrix, so Pij will depend on which cells of the matrix? So if I kind of draw a picture, right, let us say that I have, so this is my ith row, let me just let me draw it over here. Okay, and this is, let us say, my jth. Okay, so this is my Pij. What does it depend on? So I have the I minus 1th row over here. So of course it will depend on the previous cell. Okay, I mean, huh? I'm sorry. I j minus 1, this one. How? No, so if I have to decide that what will be the, I mean, what will be the contents of this cell? Okay, so the for the contents of this cell, I have to set three things: the current head position, the current letter, and the current state. Okay, what does it depend on? Yes, but suppose let us say the head is pointing to some position over here, this cell. Which cell? This one. No, see, if it is actually something which is let us say beyond j minus 1 or after j plus 1, then it cannot affect this, and whatever was here, the same thing gets copied over here. Okay, so the state, only the neighboring cells will decide whether the value changes or not, whether that character changes or not. Okay. So basically it will depend on just these 3 cells, okay, that is j minus 1th cell, jth cell and j plus 1th cell. Okay. So Pij depends on, or depends only on P I minus 1 comma j minus 1, P I minus 1 comma j and P I minus 1 comma j plus 1, only these 3 cells. Okay. And exactly how it depends on, what is the dependence, we can characterize that as well. How do I write this? Okay. So we build a constant sized circuit, let us call it Cij, as follows. So, if the head present bit of P I minus 1 comma j is set, then look up the circuit C delta to find the data part of Pij. Okay. So, suppose if for this cell the head present bit was set, okay, that means it was set to 1, okay, it means that the head was pointing over here. Then I just look up the function C delta, that is whatever was the current state in Pi minus 1j, and whatever was the current letter in Pi minus 1j, I just feed it to C delta and I get what q prime and a prime I get, and I just put it over here. Okay. So, that is the data part. Now, what about the left right part? Okay. So, I mean what about the head present bit? Huh? I am sorry? No, I am talking only about the data part of Pij. So, if the head present bit of this is set, then this is how I compute the data part of Pij. But what about the head present bit of Pij? Say it again.
So, if the C delta gives me left,
C delta on what? Of what?
on the whatever the Pi minus 1j contents are, if on that content the C delta outputs left, then the Pij content remains intact.
No. No. So, if the head present bit of this is set, okay, which means that, huh?
Pi minus 1 j, okay, okay. I was thinking about j minus.
No, not j minus 1, pi minus 1 j. So, if let us say the head is pointing over here, it means that I have to apply the Turing machine, I have to apply the transition function on the data part of this cell, right. So, I look at this, the state over here, the letter over here, I apply it and I get q prime and a prime for Pij, okay. That is it, I do not look at whether it is going left or right immediately. Now, I have to set the head present over here. Now, how is the head present bit set over here? So, the head can come to this position either from here or from here, right. Huh? From pi minus 1 j, from pi minus 1 j it will go to either here or here, but it will not come here, okay, but I do not care about that, I just ignore about that. When I go to these two cells, then I will figure it out. So, now the remaining point is, now if the head present bit of p I minus 1 j minus 1, if the head present bit of this or p I minus 1 j plus 1 is set, then look up C delta to find if the head comes to the ith cell. Okay. Now, the head can come to the ith cell only from either I minus 1 or I plus 1. So, if the head position bit of either these two entries were set, you look up both those entries. Okay. So, look up pi minus 1 j minus 1, apply again C delta on the contents of this and see, now you check whether it is going left or right. So, from this if it is going right or from this if it is going left, then you know that the head present bit of Pij has to be set to true, otherwise not. That is it. So, this allows us to compute Pij for each and every ij. And the reason why this is a constant sized circuit is because I am looking at only 3 cells, okay. Each of these 3 cells have constant amount of information and I am able to compute it. Okay. So, now what remains? So, here what we are doing is kind of an iterative step, right. So, to get Pij I am looking at Pi minus 1, but how do I get the contents of the first row? There is no 0th row, right. So, the contents of the first row will be basically dependent on the input, okay. So, for the first row of P, the first n cells contain the input x and the current state of P11 is Q0 and the head present bit of again P1 comma 1 is set, everything else is set to false. This is set to true. When I say set, I mean set to true, everything else is set to false. This we are doing because we assume that at the beginning, as I said, we assume that the head position is at the first cell and the tape contains the input x. That is exactly what we are characterizing. This we can actually look up the input. So, we know what, so given any x we can actually design this, and now subsequently for every I greater than or equal to 2 we can build for Pij. And when do we accept? When do we accept? When we reach some accept state, right. So, how do we know we have reached an accept state? So, basically we can take an OR of the following. So, for, well, yeah, so the definition of acceptance of a Turing machine is whenever it reaches an accept state we accept the input, we do not care what happens after that. So, basically we can take an OR of all the cells whose head present bit is set. Okay. Well, actually there are, okay, so let me do it in a different way. So, let us do it in the following way. So, look at the Pnth row. Okay. So, if the cell whose head present bit is set contains an accept state, then yeah, I mean it is okay, then accept. And one other thing that we need to mention over here, because we are looking at the Tnth row, is the following, that assume without loss of generality that once M enters an accept state, it stays there forever. You can modify the transition function to make sure that from an accept state it does not go to any other state. So, therefore, we know that if it had entered an accept state at any row, it will remain at an accept state in the last row as well. Okay. So, this is, yeah, I mean more or less the entire proof. So, what have we got as a result? That if I take a Turing machine which runs in polytime, then it can be simulated by, let us say if it runs in n to the power k time, it can be simulated by circuits of size n to the power 2k, which is again polynomial. Okay. So, P is in P/poly. In this circuit, we are computing all the contents at each step. Yes. Yeah, the entire matrix we are computing. Okay. So, now actually this computation can be made more efficient. So, instead of taking Tn square, there is a result by Schnorr and Pippinger, who showed that you can actually simulate in time in size Tn log Tn. Okay. And that kind of uses the fact that, well, you do not have to look at the end, you do not have to store this entire thing, okay, because from 1 you only go to these 3 neighboring things. So, you can actually make what is, you can make the Turing machine into an oblivious Turing machine. So, an oblivious Turing machine is a Turing machine whose head position does not depend on the input. Okay. So, for every input of a fixed length, the head position is the same at any time step j. So, you can actually make the Turing machine into an oblivious Turing machine, and then you can show that for an oblivious Turing machine this can be done by a linear size circuit, and to make a Turing machine into an oblivious Turing machine there is a blow up of log n. So, that is a more that is a better upper bound, and that is the best that is known. Okay. Okay. So, when you say P slash poly uniform, what do you mean? So, you mean let us say what kind of uniform, log space uniform or P. So, if you say P uniform, what does that mean? That means that there is a polynomial time machine which given n can generate the circuit, and now then it will become equal to P, because then what you can do is that you can generate the circuit, and on any input you can actually kind of do a traversal of this circuit in P, and you can find out whether it is accepting the input or rejecting the input. So, that is the other side, but that is possible again. So, traversing a circuit, so given a circuit and an input, so this is called the circuit evaluation problem. In fact, again this is an interesting result, that this circuit evaluation problem, so the circuit evaluation problem is you are given some circuit C and you are given an input X, and the question is, does C accept X? So, this problem is not just in P, it is actually P complete as well, it is hard for P as well. Okay, so, entire P reduces to this. So, by this result it shows that, well, if you take any notion of uniformity for P slash poly, then it is equal to P. Okay. So, any other questions? So, one more point which I must mention over here before we move forward is the following, that so this is actually one way to define P slash poly. Okay. So, you might see books or references where there is another notion of defining P slash poly, which is the following. So, okay. So, what we will look at is Turing machines that take advice. Okay. So, what is this? So, a Turing machine is said to take advice if in addition to its input X, it takes a string alpha mod X as input as well. Okay. And the point to be noted here is that, note that alpha is the same for all inputs of a fixed length. Okay. So, alpha is a function, okay, which depends only on the length of the input, okay, it does not depend on the actual input. So, a Turing machine is said to take advice if in addition to its input, it has a string that is available to it. And now what we can say is, we can give the following equivalence, that P slash poly is the class of functions for which there is a polytime Turing machine taking an advice of polynomial length. Okay. So, you can write the formal proof as an exercise, but the idea is very simple actually. So, given a problem in P/Poly. So, what is P/Poly? P/Poly is essentially a family of circuits, okay, which have polynomial size. Now, what I can do is that now each circuit I can encode it as an advice string. Okay. So, the circuit will have polynomial, each circuit has length that is polynomial in n. So, I can encode it as the advice string of that particular n. So, Cn is essentially the advice string for this Turing machine. And now this Turing machine with the circuit, as I said, we can just simulate the entire Turing machine, simulate the entire circuit, and that will be the output. That is one direction. The other direction is, suppose you are given a Turing machine which runs in polytime and also has a, also takes an advice string of polynomial length. How do you show it is in P/Poly? What is the idea? Exactly. So, no, I mean, how do you build the circuit? So, the circuit is basically just this simulation, and you just hard code the advice into that circuit, okay, because it is just one advice string for the entire circuit, you can hard code it exactly. Okay, so this kind of shows that P is in well, yeah, P with polynomial advice is the same as P/Poly. So, now the next question is that we have P in P/Poly, how big is P/Poly? Of course, we know that these classes have these are non-uniform classes, they have undecidable problems. So, we cannot expect that they will be equal or anything even like that. They are not even, for example, there are even beyond exp in some, well, not beyond, but there are problems in P/Poly which are not even solvable by any Turing machine, forget exp and exp whatever. But can I say at least the following? So, well, if P is not in P/Poly, the next question that arises is what is the relation between NP and P/Poly? For example, can we say that NP is in P/Poly, or can we say that NP is not in P/Poly? So, when I say NP is not in P/Poly, what I mean to say is that is there a function in NP which does not have polynomial size circuit. So, we know that every problem in P has polynomial size circuit, but can we say the same thing, I mean, can we refute that for NP? And now, because well, yeah, P is a subclass of P/Poly. If we are able to prove this, what would that imply? This would be another way of, this would be one way of showing that P not equal to NP, okay. And this is something that we again kind of, we hope it is true, not we just hope, but we believe it is true, because well, NP has very complicated problems, I mean problems where we have to kind of, we can only verify solutions, right. So, how can we design polynomial size circuits for it? It seems quite unlikely, and there are even results which show the following, okay. There are results which show that if NP is in P/Poly, then there is some de-randomization that happens, okay. So, that is quite unlikely. So, therefore, what researchers tried to do is that in trying, well, they tried to see that, well, can we relax this problem, okay. So, instead of showing NP is not in P/Poly, can we at least argue that NP is not in even some smaller size circuits or some smaller depth circuits. So, here the depth can be arbitrary, the depth can be as large as polynomial. Can we for example argue that it is not in constant depth circuits. So, for constant depth what is known is if we move to constant depth over here. So, we have for example AC0 and there is this famous result by several people. So, first it was shown by FSS that the parity function, or I can also call it as the mod 2 function, is not in AC0. Okay. So, this result was shown by first Sachs and Sipser in I think 81 first, then independently it was shown by Ajtai in 83. So, they showed that well parity does not, so if I look at a constant depth circuit for parity, then it would need super polynomial size. Okay. Then Hastad basically improved this and showed I think in 84 or 85 probably, I do not remember. So, Hastad showed that not only will it require super polynomial size, it will require exponential size. Okay. And his idea was to use this random restriction. So, we saw random restriction when we were proving Subotovskaya's theorem. Okay. We will again revisit this result and we will show that any circuit which computes parity with constant depths will require exponential size. So, then the question was what if we go beyond parity, or for example what if I kind of look at functions which are more difficult than parity. Okay. For example mod 3, mod 4, and what happens if I give those gates for free to my circuit. Okay. So, what Razborov showed is that if I look at for example mod 3 cannot be computed by AC0 circuits plus mod 2 gates. So, even if I give mod 2 gates for free to the AC0 circuit, it cannot compute for example mod 3. Okay. And Smolensky actually generalized this and showed that well if I want to compute some mod P, this is not possible with AC0 circuits plus some mod Q gate where P and Q are co-prime. So, if I take let us say for example 5 and 7 or even 5 and 6, if I give let us say mod 5 and okay let us take 5, let us take it for primes for the time being 5 and 7, then mod 5 cannot be computed if I have mod 7 gates. Okay. So, the next thing is that well let me just say it for prime for the time, just co-prime where P and Q are primes. Now, the next question was what if I give let us say both mod 2 and mod 3 gates. Okay. That is basically I have mod 6 gates present in my circuit. What kind of functions can it not compute? Okay. So, Barrington posed this open question that well if you look at the threshold function. Okay. So, this was an open question. So, threshold function is not in this class ACC, or just I can call it ACC. So, what is ACC? So, ACC is basically the class of all functions for which you have and or not and any mod gates. Okay. You can take any mod gates that you want. Okay. And it is even kind of hard to compute threshold functions with this. Okay. So, this proved very difficult to compute. So, the question was generalized further that instead of let us say threshold function, what if I choose let us say a function in NP, okay. Take any function in NP, any problem, let us say the clique problem or Hamiltonian path problem, and can I show that well Hamiltonian path cannot be computed by an ACC circuit. So, again just think of ACC, it is basically a constant depth circuit which has AND or NOT and any mod gates. That was also not known, okay. So, for NP also it was not known. So, this is a question whether it is in ACC, okay, and not just NP. So, if you go, so let me write these classes over here. So, these are the complexity classes. So, you have, well, let us say threshold function, then I can go to NP, I can go to NEXP. Even we could not show that there is a NEXP function which is not in ACC. The best that was known is there was this class, well the first thing that was known is if you have something in EXP to the power NP to the power NP. So, this powering means that you are taking an oracle gate which is a some NP function, then there is a lower bound. In fact, there is a very large lower bound that there are circuits of size, I mean there is a function over here which cannot even be computed by circuits of size 2 to the power n by n. That is roughly what we get even by Shannon's theorem, okay. So, there are actually, So, NP to the power NP is basically I have an NP machine which is taking NP as an oracle, let us say which is taking SAT as an oracle. Yes, that class is more powerful than NP because for example, it can compute co-NP, it can compute problems in co-NP because I can directly give it a SAT instance and I can get whether it is unsatisfiable or not, but NP is not known to contain co-NP, okay. Yeah. So, but anyway we will not be even getting into these things for the time being. So, this is the thing. So, the point is that up to this level we had no idea, the only thing that we know was for very large class of functions. So, this was kind of like even embarrassing in some sense that we have such a large class, a complexity class, but we can't even show that there is a function over here which is not in ACC, and this was shown by Ryan Williams in 2010 I believe. So, Ryan Williams showed that NEXP is not in ACC, okay. So, 2010 he exhibited a function, but again that is kind of the best that is known. So, I am just trying to give a roadmap of what we will be doing for the remainder of this course, okay. So, as I said we will be looking at Hastad's result of random restriction, we will also look at Rasborov's, Smolensky's way of showing these results, these lower bounds, and this is basically by a very different method called approximating polynomials. So, we will design approximating polynomials for these various gates and then show this, and then we will towards the end of this course we will try to look at this result by Williams, okay. So, that is all that I have for today, okay. So, the last few weeks we have been in some sense looking at upper bounds, we tried to design circuits for various problems, we designed circuits for these arithmetic operations, efficient circuits, we showed relation between circuits and complexity classes. But now for the rest of the course, more or less for the remaining part of this course, we will be looking at lower bounds. We will try to see that why or how we can show that certain functions are not computable by certain circuits. So, ACC is basically constant depth circuits of unbounded Fanon that consist of AND or NOT and mod k gates for any k. Any k. Mod k gates is basically a mod k gate will evaluate to 1 So, it has input, let us say a mod k gate takes input bits x1 to xn. So, it would evaluate to 1 if sigma xi is let us say congruent to 1 mod k. You can define it anyway and it will output 0 otherwise. Yeah, you can have mod n gates also.
So, but I think the thing that requires that there is a finite set of moduli for which gates are allowed for a given circuit family. Like for a particular function, all the circuits for that family should have moduli from a fixed, constant size set of allowed moduli. This is actually equivalent to saying that there is just one modulus, but I don't think it can be allowed to be arbitrary.
I thought it can be allowed to be arbitrary. Yeah, so k, okay, maybe you are right. Yeah, I have to check. So, yeah, k does not depend on n. So, what you are saying is that this k is bounded. So, you can only allow mod gates up to some constant, and that can be replaced with a single mod gate of for some other k prime. Yeah.
So, but if we are doing that kind of stuff, then I mean these kind of results are already showing that if we are allowing some mod k gates, then we can't compute certain other things.
If you are allowing mod k gates, then we can't compute what?
Like mod this thing like.
How do you show? You are giving it more power, right?
No, sir, you said that these results are mod 3 to
Yeah, so this is for very specific things. If 3 and 2 are primes, then this is happening. But what if I allow mod 6? Then I can compute mod 3 very easily.
So, isn't there any extension to this result, like O primes or something?
So I have to just verify. So I thought it was true for co-primes, but it is for co-primes, yeah.
So, then if it is co-prime, then suppose we allow mod k gates, then there will be some number which is co-prime to k.
Huh.
So, then we can't compute the mod of that.
Yes, you can't compute by that same result. But it still does not say that, for example, if I take the threshold function, threshold is basically outputting 1 if the sum is greater than some k, whether you can compute this simple function.
So, then but that modulus will be in NP, right?
Which modulus?
That mod k, any mod k gates, not this mod k, it's NP.
Yeah, they are in NP. Mod k are in P, in fact. But you are looking at the other now. You are trying to simulate ACC using an NP machine. But that to anyway is not possible because you are looking at non-uniform things here and you are looking at uniform things here. So you can of course simulate any mod using a just a linear using a log space Turing machine as well, right? But what about the non-uniformity? That non-uniformity cannot be done, right? We are looking at the other direction over here, that what questions in the uniform world cannot be solved by a non-uniform circuit which has very small depth.